Welcome to the lecture series on vitamins and nutrition. Today we are going to discuss about the physical and chemical properties of vitamin C. We are also going to look into more details of how vitamin C participates in collagen synthesis and how vitamin C exhibits its role as an antioxidant enzyme. If you look at this slide, we have just recaptured what we have done in the earlier discussion. We know vitamin C is a water soluble vitamin. It's a strong reducing agent and it is very important for all the reversible reactions where vitamin C is oxidized to dehydroascorbic acid. Now, if you look into the functions of vitamin C in terms of collagen synthesis, we know most of the proteins have to undergo post-translational modification. So, what do you mean by that? Many functional proteins have to be chemically modified before you realize the function of such proteins. Such kind of chemical modification would help proteins perform their function in a better way. I can take this example. Let's look at a two-wheeler being manufactured. So, the actual two-wheeler being manufactured would contain the core parts of an engine and related accessories, but probably you cannot run the vehicle directly on road. You need many extra fittings, right? Some extra fittings are mandatory where you have to add them, let's say Sarigod and the fitting that is there that helps skid the vehicle, prevent skidding of vehicle, and many such extra fittings we do. But only when you have all these fittings intact, apart from the major parts of the vehicle, your vehicle is not thoroughly functional. So, most of the post-translational modification can be associated that way. A protein immediately being churned out from ribosomes may not be completely functional to perform its role. You need some additional conjugation reactions happening upon the protein that would make the protein more function worthy. So, if you look at this slide, it tells you how post synthetic modification of procollagen to collagen is essential to make collagen as an essential protein as part of the connective tissue. And you do have two enzymes, proline hydroxylase, lysine hydroxylase. Proline is an amino acid, we know, but hydroxyproline is a derivatized amino acid. Similarly, lysine is an amino acid and hydroxylysine is a derivatized amino acid. In a normal protein construction, you find these amino acids proline and lysine finding their place. But if you find hydroxyproline and hydroxylysine, immediately you should sense that these amino acids have undergone post-translational modification. Now, the question is whether they are post-translationally modified and then incorporated, or is there a chance by which the protein is synthesized and then the side residues are hydroxylated. Either way, you require vitamin C, and different pathways are engaged in perfecting this conversion from procollagen to collagen, and you do see here how vitamin C is extremely essential. You know very well vitamin C as a hydroxy group and how they are able to transfer these groups across the protein in its functional role of being converted from procollagen to collagen. Now, in both these cases, what is the role of vitamin C? Vitamin C acts as a cofactor for these two enzymes. So, if you have inadequately hydroxylated precursors cannot acquire stable helical configuration and cannot be adequately cross-linked. So, they are poorly secreted from fibroblast. See this statement, it tells you that how hydroxylation is an important feature in the coiling of protein. You know, collagen, especially the helical conformation of collagen, the triple helix, is extremely important for the structure function role that these residues play in the final conformation of collagen. So, collagen is an interesting protein, and collagen provides the stability for all the connective tissues across our body, especially the tendons across joints and the cartilage fragments everywhere. So, without this hydroxylation happening and ensuring the helical conformation in its proper perspective, there could be lots of structural damage across the connective tissues, and that is what we typically witness in vitamin C deficiency, and this becomes a cumulative event that eventually results in scurvy. So, you see, for people who suffer from scurvy, do not have vitamin C in their diet to adequately enable them to carry over these reactions, and because of this they suffer from this bleeding condition called scurvy. So, the secreted fibers lack tensile strength, are more soluble and are more vulnerable for enzymatic degradation. See, one thing we need to remember, the connective tissue is always there in a dynamic state. So, there would be wear and tear across the connective tissue because of movements which needs to be promptly fixed, repaired and maintained. Now, if you do not have the sufficient raw material to do this process, you know naturally what will result. There would be more damage than more restoration happening, and eventually that will result in laxation of the joints and the tendons, and that would further aggravate the inflammatory process. So, lack of vitamin C leads to suppression of the rate of procollagen peptide synthesis. This is grave. If this is going to happen for a long period of time, you find the person completely losing its ability in properly constituting the collagen fibers in the right way, how the collagen should hold as a tensile strength anchor, and you find they are now incapable of doing such function. That could be directly attributed with vitamin C deficiency, and as I told you earlier, all these effects are cumulative over a period of time, and once the damage is done, yes, it takes months to really repair back with proper dietary supplementation of vitamin C. And I would say scurvy is that way a very painful condition. So, collagen contains the highest amount of hydroxyproline. So, as I told you earlier, so you see there in the blood vessels there would be lots of hydroxyproline deficiency leading to an disarray in the vasculature, and there could be spontaneous hemorrhages in scurvy. So, we know whenever there is a vasculature which is being damaged either because of wear and tear or maybe pathogenic invasion, our body would immediately try to fix the condition, and it would make use of vitamin C for its function, providing good raw material of collagen to do the job. But if you look at in cases with vitamin C deficiency, the quality of collagen which is available for the repair mechanism would really be a problem. In this case, it would eventually lead to spontaneous hemorrhages as one of the major symptoms in scurvy. So, you see there in this example how vitamin C plays an essential role in wound repair, in the healing of gums, and primarily for immune function. Whenever you look at any kind of connective tissue repair mechanisms, immediately you could associate the role of vitamin C behind the scenes. So, vitamin C participates in all such activities so that there would be constant repair and maintenance going on at every stage of tissue repair and development. So, you see all these three areas are being directly affected by vitamin C deficiency. And you also look here how proline hydroxylase is required in the formation of C1q component of the complement. Sometime before, when I was explaining the role of vitamins in the complement pathway, I also explained a little bit on complement. I would like to refresh that over here. What is this complement protein? We lack this I. If you look into the spelling, it's COMPLEMENT. So originally they brought up this idea as complement to the normal existing antibody function. This is a non-specific immune response, but can be made specific when it's going to involve plenty of immune cells in focusing a membrane attack complex formation. So complement pathway primarily ends up in clearing the pathogens as soon as possible once they find their entry into systemic circulation. They don't give a chance. Complement is so rapid, but it's a series of enzymes that go stage by stage in activation and eventually leads to membrane attack complex of the pathogen and would leak the pathogen and would remove the pathogen. So you see there in this C1q, we have the first initiating component, C1q, C1r and CNS. Although it's not mentioned here, C1q is one of the component without which the first initiation step in the complement activation will not kickstart. And you need proline hydroxylase for the component C1q. Not only participating, if you don't have adequate C1q, obviously we know the complement pathway cannot be initiated, and that's what happens in vitamin C. Now you understand how vitamin C has a role in immune function. It's not only membrane stabilization by providing adequate collagen raw material for the vasculature and for lymphatic vessels and so on, but also plays a role in the synthesis of complement proteins like C1q. So lack of vitamin C would have impact in both innate immune response and adaptive immune response. And we also look here how vitamin C plays a role in proline hydroxylase function, and proline hydroxylase is essential in the formation of osteocalcin and how they play a role in the calcium metabolism. And we have seen when we studied about vitamin D, how vitamin D is extremely important in the homeostasis of calcium and in the maintenance of bone. And you see over here in this example how vitamin C closely is associated with the metabolism of calcium and with osteocalcin, and all together help in the maintenance of bone, in the repairing and regeneration of bone. Now one more point to mention. If you recollect, sometime before we have looked at how vitamins can also play an essential role in the synthesis of neurotransmitters. So what are neurotransmitters? So neurotransmitters are chemical messengers between neurons for chemical transmission of impulses. So you do have transmission of information happening across neurons, and the transmission of impulse can result by direct electrical conduction, and majority of the neurons also utilize chemical modes of transmission. So that's what we understand by the synaptic junction between two neurons, and between these synaptic junctions you have the neurotransmitters secreted from one neuronal end and being received by the receptor on the other neuronal end. There are important neurotransmitters. The example we see here, dopamine, noradrenaline and adrenaline, belong more to catecholamine category of neurotransmitters. So what cytokines would do between immune cells, neurotransmitters, they do the same thing between neurons. And we have seen how vitamin C is essential in the tyrosine amino acid homeostasis, And since these amino acids are the key raw material for dopamine, noradrenaline and adrenaline synthesis and maintenance and recycling, and vitamin C is essential for this, it's all linked. So we could say all these catecholamines, because their structure resembles catechol, that's why it's called catecholamines: dopamine, noradrenaline, adrenaline. So we could make a statement like this: vitamin C is essential for many catecholamine neurotransmitters. So if you look at, if a person is going to run down on vitamin C sufficiently, this will have an impact on the neurotransmitter synthesis. So if people complain of tingling sensation, periodic numbness because of these neurotransmitters, lack of reactivity, let's say for example adrenaline. Adrenaline is one of the key neurotransmitter as well a hormone, keeping a person ready in times of crisis. And if we do not have vitamin C, our ability to mount such responses would be directly affected, and a person will not be in a position to respond to alarm, respond to threat, respond to any kinds of damage connected with any threat that would face a person. So you understand. So vitamin C creates a kind of a panic state. The person is not able to like really respond to stimuli. And we are going to look into little more into the structural aspects of vitamin C. So far, whatever discussions we have made clearly tells us how vitamin C plays an important role in various metabolic functions. We saw in a very systematic manner how in collagen synthesis, how the hydroxylase enzymes, proline hydroxylases are key, and how vitamin C, being a cofactor, tries to control the synthesis of all these essential components. So here we look at a 6-carbon lactone and 2,3 endiol structure. So this is the same structure what we have already explained for vitamin C. And if you look at what kind of transition it undergoes, so this is vitamin C. Here you have semide dehydroascorbic acid, then we have dehydroascorbic acid. So it's in a 2-stage transition step. So eventually we have dehydroascorbic acid. So if you look at the nomenclature of vitamin C, although we have seen vitamin C being a chief vitamin for all these reactions that we have discussed so far, we also look closely what exactly is the chemical identity for these vitamins that belongs to vitamin C category. We have a generic descriptor. What do you mean by generic descriptor? You could have all the compounds that can be grouped under vitamin C category. So the actual compound being L-ascorbic acid, and the designators help us technically look at what exactly this compound is chemically. So it's chemically 2,3 didehydro L-3O hexano 1,4-lactone. So we have this oxidized compound called L-dehydroascorbic acid or dehydroascorbic acid. So this kind of discussion helps us understand what chemically vitamin C is made of. Looking into the functional names of how vitamin C is depicted in a chemistry literature, we would be in a better position to understand how vitamin C, acting like a cofactor for these important enzymes, is able to carry forward its function. So what is exactly, as we know, as the word says, it's an ascorbic acid. And what is a carbohydrate? In this case glucose. I have given you this definition earlier. So glucose is polyhydroxy compound with the keto functionality or a carbonyl functionality either in the hemiacetal or hemiketol form. and this being the raw material that results in ascorbic acid, and you could naturally expect that ascorbic acid having a pKa value of 4.1 and 11.8 depending on the functional groups present on them. You have the enolic hydroxyl groups are capable of dissociation. So, you look at enol and keto form, and this is a common feature for all carbonyl compounds. The enolic form will have the hydroxy group and the keto form would have discharged the hydroxy proton group. So, being an acid, it can participate in the formation of salt. So, you could make them as a sodium salt or a calcium salt, and those sodium or calcium salts of vitamin C or ascorbic acid demonstrate better solubility, and they can be good salts, and they are very useful in formulation exercises. And in solution, by virtue of its ability to release protons, they are strongly acidic. In some of the food industries, so this property of being used as an acidifier would add to the overall flavor when you use vitamin C. So, vitamin C has different roles to play. So, it makes the environment acidic, and above all, possessing an enolic hydroxyl group would enable vitamin C to perform such tasks. And the pKa values clearly suggest that vitamin C is a dibasic acid. And we saw this, how vitamin C getting oxidized to dehydroascorbic acid via the radical intermediate. So, this step is very important in terms of scavenging the free radicals. So, we have this semi-dehydroascorbic acid, which is also known as monodehydroascorbic acid, playing an important free radical intermediate source when you have this transition of free radical scavenging that happens through vitamin C. So, semi-quinoid ascorbic acid radical is a strong acid. So, losing a proton, it becomes an anion, and owing to resonance stabilization, it is very inert because you have a cyclic ring, but disproportionates to ascorbic acid and dehydroascorbic acid. So, you do have an intermediate compound that eventually becomes ascorbic acid and dehydroascorbic acid. So, that is why the chemistry of vitamin C is very interesting to study, as we have noticed here. In a reversible redox system, now we are going to highlight how vitamin C plays a role in the redox pathway, or acts like a free radical scavenger, or how it exhibits its antioxidant property. So, you have these three: ascorbic acid, semi-dehydroascorbic acid and dehydroascorbic acid. All these three are extremely important in terms of the reversible redox system that they participate. So, all these three are capable of performing the function, which is very important in terms of its role in scavenging the free radicals. We are going to see one by one. It acts like a quencher of free radicals such as the singlet oxygen, and in a different case it reduces the ferric to ferrous and the superoxide radical to hydrogen peroxide. It is oxidized to monodehydroascorbic acid in all these processes. So, you see there in this system how vitamin C acts like an effective free radical scavenger. So, you would appreciate how vitamin C in a real in vivo system inside the tissues are able to do this job in an effective manner. So, that is one of the reason why vitamin C being supplied as a nutritive additive and acts as like an aid in scavenging these free radicals, because these free radicals when left unchecked can initiate lots of inflammatory processes leading to membrane damage. So, in all this case, it acts like a sentinel in scavenging all these free radicals which results as part of the normal metabolism. So, one reason when people have a dietary supplement of vitamin C taken in the form of fresh food or fruits would be able to effectively handle this kind of mechanism of scavenging free radicals. So, you look at this picture where ascorbic acid can complex with disulfides and the oxidized glutathione and cysteine, but does not reduce those disulfide bonds. This is something very interesting to notice, because we know glutathione, cysteine groups are their own right and are being used in antioxidant reactions. But ascorbic acid can complex with these disulfides but does not reduce those disulfide bonds. This is very important thing to note, because taking a vitamin C supplement along with this or in a natural setup when we have glutathione and cysteine residues in our normal physiology, how vitamin C can complement the functions of glutathione and cysteine. We also look here that dihydroascorbic acid is not ionized in environments of weakly acidic or neutral pH. So, this is a feature that we need to know, because some of the carbohydrates also have a complexing ability, and vitamin C's function can also be attributed to its complexing ability. And being relatively hydrophobic and the vitamin C is able to penetrate well the membranes. Okay, so we see here the ascorbic acid form and different versions, how their relative switch in the chemical structure decides the bioavailability features of vitamin C. So, in this slide we see an aqueous solution of dihydroascorbic acid appears to be very unstable and is degraded by the hydrolytic ring opening to yield 2,3-dioxo-L-gulonic acid. So, the dihydroascorbic acid reacts with several amino acids to form a brown colored products, a reaction contributing to the spoilage of food. If you notice some of the fresh vegetables and fruits that we got, after a period of time they appear brownish in nature, and there are many reasons could be attributed. So, one of the chief reasons being the vitamin C content in them has resulted in the production of these substances, especially if you are going to have many amino acids. These amino acids are going to get converted into colored brown products. Now you can have a clue of why this turning of color that you notice in fresh fruits and vegetables can be directly associated with vitamin C function. So, dihydroascorbic acid is the one which initiates the process. So, we could say how fresh the vegetable was by looking into whether there is any brown colored products being formed. If they are formed, then the vitamin C content has already started reacting with the amino acids present in the substance. Here you find a relative biopotency between the classes of vitamin C compounds available. Ascorbic acid has 100% functional role. You have ascorbyl 5,6-diacetate, one more derivative of vitamin C is also good. Similarly, ascorbyl 6-palmitate is also really good. Now, why we have to look at this? When we are in the job of food nutrition analysis, and when we want to preserve the nutritive content of a food in terms of vitamin C, being aware of these compounds would enable us to determine how efficient a particular product would be in preserving its vitamin C potency. If you have dihydroascorbic acid levels high, so it means it's of little deficit in the actual vitamin C content. Same is the case with 6-deoxy ascorbic acid, and you see there isoascorbic acid and L-glucoascorbic acid. The moment they go to that level, and if their proportion is high, then probably the functional biologically active vitamin C is no more there in the food. So this is one way, an indicator to tell us the nutritive content of a food in terms of vitamin C. We are going to quickly summarize. So what all we have seen today? We have seen the different vitamin C derivatives and their functional role, the physical and chemical properties of these derivatives, how they participate in a free radical reaction, and how the free radical reaction is carried through, and we also saw the relative potency of vitamin C derivatives. Though this will give us a better command as to the functions of vitamin C and how these compounds can be effectively fortified in the food products and the nutrition that we consume. And I am going to conclude with some questions. So you can take down these questions. What is the role of vitamin C in the free radical mechanism? Enumerate different vitamin C derivatives and give a note on the biopotency of different vitamin C derivatives. So today's series we had looked into different physical and chemical properties of vitamin C, and hope this was useful for you. Thank you for your active participation.